All right, good morning, ladies and gentlemen. Do this now in your notebook. Pause the video and give it a shot. Review from yesterday. Okay, you pull a wooden block.
This looks pretty easy to me.
It is 0.75 meters across the table. Okay, so let me just go drop. So blocks here, and we pull it this direction. 0.75 meters, so distance is 0.75 meters. Okay. If the average force is 8.3 newtons, how much work do we do?
What does average mean? Means that sometimes it's more, sometimes it's less, but the average is that.
Okay, so overall average was 8.3. So my force is in this direction, my displacement is in this direction. I can just say work equals force times displacement, yes?
Yep.
Okay, so my force was 8.3 newtons times 0.75 meters. My work is going to equal 8.3 times 0.75, 6.2, we'll call it.
Sweet.
6.2 newton meters or
Joules.
Is that what you guys got?
Sweet.
So, okay. Page 227. It says scan first, then read. So I want you guys to go to page 227 in the e-text, and we are going to start reading right here. It says constant force at an angle, and this is how I want you to read. I want you to use this strategy that I give you. The first thing you're going to do is scan the paragraph. What does that mean? Well, you're going to read the first 3 words of every sentence, and then you're going to stop. So I'm going to say, you've learned that, and then I'm going to stop until I get to the next period. Okay, right there. Then again, I read the first 3 words. A force exerted, and I'm going to scan to the end of the sentence. Okay, for example, what? I'm going to scan, and so you see how I'm doing this?
Yeah, the idea is that you're not reading yet. You're just looking for the first 3 or 4 words from each sentence and then finding the period.
Mm-hmm. And we're scanning so that, and through the whole paragraph first so that we get a big picture of what's going on.
Yeah.
Then we go and we actually read, you're going to be like, oh, I totally understand where this is going. And we talked about this yesterday. This is the lawnmower.
Figure 10-4, and it asks you to look at 10-4.
Yeah, so when I ask you to look at it, make sure you look at it. Okay, so do that first.
Pause the video, and we'll be back in a minute.
Yes. Okay, we're back. Okay, so review. Work equals force times the cosine theta of the displacement. Units, newtons in meters, and so this is a joule, NMJ.
And this is different from the equation that we used in the do now, because the do now is a special situation where the force and the displacement are in the same direction.
Very good point. So this is the force, this is the displacement.
But it's not always in the same direction. There's an angle between them.
Exactly. Sometimes the force might be this way and the displacement is this way, like with a spring.
Or anything in between.
Yeah. And so that is why we have to include this or, yeah, and we're going to talk about another example today of when you have to use this. Work is how much force is exerted on an object times the displacement it moves in the direction of the force. That's where that cosine theta comes in.
Yep.
Okay. Just a definition. Let's do a lab. Work done against friction lab. So this is what I want you to do for this lab. The first thing you're going to do is make a sketch of the lab setup, which we'll show you in a second. And then you guys are going to record the data that I give you, and then you're going to do the calculations, showing me everything, and then answer all of the questions that we talk about after. Okay. So here we go. Oh, let me go ahead and get my thing. Okay. So.
You should do it on this side.
Oh, that's a good idea.
Do-si-do. They don't know what do-si-do means.
Okay, so trial 1. So with the 1 kilogram mass in the front hole of the black box, of the black block, pull the block 0.5 meters horizontally with a constant force at a constant speed.
So here's the block.
So this is the block right here. My 1 kilogram mass, it's starting right here. And I'm going to pull it to the front, gets right here. And my goal is to pull it parallel, horizontally, right here, with a constant force. And see if we can figure out what that force is going to be. Here we go. Here we go. I'm at 6. Right there. Okay, I was at 6 newtons for that.
So that's 6 newtons.
Okay. Jot this down in your notes, you guys. Okay, so force, we said 6 newtons right here. And my displacement was just 0.5 meters, yes?
Yeah. And what's the next slide?
Use work times the displacement to find how much work you do if you pull it 0.5 meters. So you guys are going to solve this, and we just said that the equation you're going to use is work equals force times delta T. Okay,
Yep.
do it. Trial 2. Reset. Now pull with the scale 0.5 meters at an angle of 45 degrees above the table. Okay, now keep in mind this isn't a perfect 45 degrees, but we're going to call this 45.
Oh, that's perfect 45 degrees.
That's
If you ask
perfect,
me,
right?
that's 45 degrees right there.
Okay, so same thing. We're going to pull to the 0.5, and I'm going to be looking at how much force it takes me to do this. Ready? Set.
45 degrees, you're down about 30 right now.
Oh, thank you, thank you.
30, you keep creeping down. What was the average about?
That was like a 5.5.
Okay.
Okay, 5. It's hard to pull it at constant speed.
It is.
Okay, and again it went 0.5 meters, right?
Yep.
All right,
But
so
something's got to be different.
for
What's
this one, what is different? What is different for this one,
well, there's less force to go the same distance.
right? And also, how was I holding it? I was holding it at 45 degree angle the whole time, right?
Yeah, but it wasn't going in that direction. You were pulling at 45 degrees, but it was moving horizontally.
So I'm pulling this way, but its displacement is this way. Are the force and the displacement in the same direction?
Nope.
No. So what are we going to have to use to find our work?
Yep.
Boom, okay? And,
Now-
you know,
Let's talk a little bit about the components. We
Yeah.
won't need it in the calculation, but what pulling at 45 degrees is doing what?
so when I pull at 45 degrees like this, a part of my force is pulling it up like this, kind of lifting it up almost, right?
Oh, that wouldn't that decrease the normal force?
It would. And the normal force is the squeezage, right?
So you're
kind of
reducing the
reducing the-
squeezage, which would reduce the friction.
Mm-hmm. So this I'm pulling up like this, which is lifting it up, but I'm also, when I'm pulling at a 45 degree angle, pulling it this way. So it seems like we have this component and this component.
Yep.
That makes a triangle.
Yeah, yeah.
Triangle parts. Okay. So you do not need those triangle parts to do this, but the reason why we have to use cosine theta is because of that 45 degree angle with those components.
What does the next slide say?
Work equals the component of the force.
I'm salivating.
Work equals the component of the force in the direction of the displacement. Okay, so work equals force times displacement, cosine theta. We have to include the direction of that displacement.
Yeah.
Work equals the component of the force in the direction of the displacement.
You know, why don't you make a diagram and show that horizontal component is the adjacent side of the triangle?
Oh, that's a great idea.
It just
Okay.
occurred to me that might be a good thing to do.
Let me go ahead.
You can just take what you've got up there and erase the... Yeah, what the heck.
Okay. This one is not as good as this one. Okay. So I have my block. Where's my black marker?
Over here.
Oh, there it is. Thank you, sir. Okay, so we have our block, and we'll just represent it by a dot. And I was pulling it.
45 degrees.
45 degrees.
But the displacement was
0.5 degrees.
0.5 meters.
Oh, sorry. 0.5 degrees. displacement equals 0.5 meters. And so we moved it. Should I draw it under here?
Just draw an arrow, yeah.
Draw here. Displacement equals 0.5 meters. Okay.
So if we want to know the component of the force in the direction of the displacement, the force is the red arrow,
Which direction is the displacement?
horizontal.
Okay, so
What part of the triangle is that? That'd be the adjacent side.
now I'll draw this one too, but we don't care about this one as much.
That was trying to lift it up off the table. That was not doing any work.
Yeah, this is the adjacent side, like we just said. This is the opposite side because it's opposite of the angle, and this is
Yeah.
our hypotenuse. Yes.
Yeah. So that's why you, in this case, you use the cosine function.
We use the cosine because we know that cosine theta equals adjacent over hypotenuse, and we want the component of the force that is in the same direction as the displacement, and that would be this side, the adjacent side. This side would give me the opposite side, and that would be the sine. Then we don't care about that.
Yeah.
Good.
So calculate how much work you're doing using that equation.
You guys got it. Okay. Work equals the cosine of theta times the displacement. Okay. Compare the two results. So once you guys get your results for that, oh, you can put it right here.
Yeah, sorry.
Okay, once you guys get your results for that, how do they compare? Which one ended up doing more work?
So make a statement there in your notes. Just compare the results.
Yeah. This one does more work, that one does more work. What do you guys
Okay,
find?
what's going on?
Okay. Let's do a practice problem. A sailor pulls a boat 30 meters along a dock. He's pulling on a rope at a 25-degree angle between the dock and the boat. How much work does he do if he pulls with 255 newtons?
I have to do this looking down from above.
Okay, so a sailor pulls a boat 30 meters. So he's going 30 meters this way.
That's a displacement.
Yeah, oh, thank you. Put a little D there. He pulls on a rope at a 25-degree angle. This one. So we'll make it look like this.
Oh, that's good.
25-degree angle. Thank you, sir. Okay,
And how much force?
pulls with 255 newtons. Okay. How much work does he do? Okay, well, work equals, usually work equals force times distance, but is our force and our displacement in the same direction?
They're not in the same direction. You have to
No.
use that other equation.
Cosine theta d. Okay. Well, we've got our force, we've got our distance, right?
Yeah.
What are we missing?
No, you got the angle too. It's all there.
Oh, you're right. It totally is. Newtons times the cosine. What's our theta?
25 degrees.
25 degrees, and our displacement is 30 meters. Boom.
Calculator time, y'all.
Easy.
Pick up your calculator. Do this. Come
Do
on.
it. Okay, 255 times cosine of 25 times 30. Oh wait, hold on. Let's see. Times 30. And I get 221.
221. What?
Watt.
No. Not watts.
231 joules.
Joules. All right.
There you go. And keep in mind what me and Mr. Boykin were talking about earlier was that there are two components to this. Okay, the x component and the y component. And the reason that we use cosine here is just because we want to know this component, and that's the cosine.
And notice that y component, the blue line, is perpendicular to the displacement. And what's the cosine of 90 degrees?
0.
0. So no work is done by that perpendicular component. 0 work done by that.
All the work is done this way.
That's right.
Good
Okay.
point. Okay.
So
for
now they have got.
homework-
That's it.
For homework. Wait, where's the thing? Okay, I got. For homework, you guys are gonna do the assignment called "Are you gonna force me to do this work?" Right? Yeah. And it's just asking you, how much work did you do? How much work did you do? How much work? All about work. Work, work, work.
Ms. Moore, you're gonna have to change that thing to put your name in there.
All right, here.
Yeah, that for next year. Have fun with it.
You guys got it. Go ahead and begin.